Good afternoon. I'm happy that we're here. I wasn't so sure last night. I teach class from 4:45 to 7:30, and in the midst of class was when the cancellation came about, and I kept going because I wanted to get through some demos that were going to be captured on my video, and I found out how the university treats everybody the same. The buses were done running, the buildings were locked up, and I had to do extra walking just to walk all the way down to the greenhouse parking lot, which I felt like, you don't care. You just want to go home, right? I mean, my students were happy to stay and let me keep lecturing, but the place just, you know, I thought about turning in my pass because I can ride my bike or ride the bus down to U-Haul and then walk home from there. But that would have not worked for me last night because it was totally gone, which, I don't know, I'm disappointed about that. Don't count on anybody. I don't know when they stopped running, but if they stopped 5 minutes after 6 o'clock, it wouldn't surprise me. It's like, wait a minute, you don't flush the pipe that quickly. Was anybody else here leaving? I mean,
I got kicked out of the gym.
Really?
Yeah.
At what time?
I was in the middle of the stair climbing.
But no, but what time was it?
6.
Right at 6? Okay. I was just, yeah, it was deserted, but
Can't stop me.
yeah, they can stop you doing everything.
On the gym to do stair climber, and you got engineering right there, right? Like
That's right.
1,000 stairs.
That's my
But-
warm-up, and then that's my cool
But understand, he paid for it already, right?
Well,
Yeah, I know.
down per credit hour.
right?
They were going to give me a free membership because I'm a senior, over 35 years faculty member, and then they reneged on that when they decided they didn't have money in the budget. So they didn't tell me that. They just got me all excited, and then it just silently disappeared. It never showed up.
35 years, here's your prize.
Yeah, I mean, I might have used it. I don't know, but that's another story. At any rate, I spent some time. You can see at the end of the week, coming up with some innovative ideas on how to work this assignment number 2 or set number 2. So I'm going to talk about that today. I've added a problem that I wanted to add to the turn-in problems too. After I spent all that time, I figured you want to be able to turn that in. I've got my renditions of it, and that's now posted. I posted the quiz solutions a few minutes ago. I posted an update to the Python 3.7 environment setup stuff, which also applies to anybody that's running Conda or Anaconda, because I've been helping people in classes get that up and running. So there's a few things that I changed in that as well. I think I'll just point out, if you're now doing a setup, this says Conda create, and this is the link that's down in the lower right-hand column. This is creating a virtual environment, but even if you've just installed the full version of Anaconda, you need to do a Conda install Node.js, and now the newer version number is 13.0.0. And what that allows you to do, that allows you to then go on and do this line right here, where you're going to enable the Jupyter widgets and the lab manager so that you can run Jupyter Lab. You can run Jupyter Notebook probably already, but Jupyter Lab is a much nicer environment, and the pieces are there. You just don't have the ability to run the widgets, and I'd like you to have that ability. So the steps are, if you do this step that I've highlighted in blue, you will get a message saying Node.js needs to be installed, which is a JavaScript environment. And you can put the full version on your system, which is what the error message tells you to do. But I found from going to the SciPy conference that if you just install this Python package, that satisfies that requirement, and you don't have to put as big a load on your system. It's just in the Python domain. It's not for the whole system. And then you can go on at that point and do Conda install PyAudio, and then of course do this -E, which is for experimental or developmental install, and get all the helpers and things in there. Something that is coming, let's see. guess I don't want to go into that. There is a new version of everything held in a different repository on GitHub. But right now, I guess I would say keep using the one that I'm pointing you at, because that will work adequately right now. We've broken the packages apart, and I haven't really gotten totally adapted to how that all works. I mean, the team working in the Scikit DSP-Com, one of the team members took that action item 2 weeks ago, and I haven't really fully digested it at all. So it's in more than one location. We haven't pushed any changes up, so it doesn't really matter. But I'm contemplating some changes at that. So some of those changes are talked about in here. Plotly is something I'm almost ready to show you, but there's pros and cons to it, and it would be really nice to have it set up for this homework problem, but I'm going to suggest a very easy workaround today rather than having to go into Plotly. So this has also been updated, how to install Plotly. If you click this link, you will see these instructions that I put down here with some more details. What Plotly gets you that is very nice is it gets you the ability to have graphics that you have a bunch of controls, plots that you have controls with. You can move around with the cursor, you can zoom, you can do other markings on it interactively, which is pretty nice. But it takes more effort to get that installed. And then if you want to render out SVG graphics, you actually have to do a few more steps. So right now, unless you do these other steps, then your notebook doesn't render out into Typora like I talked about last week. So it's kind of a big thing to swallow, and I'm just going to lay back on that a little bit because I'm just trying to get you ramped up, but I'm not trying to go from here to there in one step. I'm trying to get you to take smaller steps. But I want you to be working on it, so that was the point of all of that. And then another thing you can do, let's see. This is rendered, I re-rendered this, but I had an older version, so I'm missing something. So now I've got a broken version. I'll have to fix that, is to put in another add-on for Matplotlib graphics. But I'll have to figure out if I can find an archive copy of that now. I know it's on a different computer, so I can get back to where I wanted to be. I pulled something from an older version. Such is the life when you have cloud repositories. Does anybody not have a cloud location where they keep files and things? Do you ever get things out of sync?
Oh, yeah.
So that's what I get. That's what I just suffered from a little bit of. At any rate, I won't say anything more about that. We will come over to this. What I want to do, though, is just get back into the Fourier transform, go through some properties and theorems, and then I want to jump over and talk about the homework problems. And like I said, the quiz, I almost started grading the quiz part, but then I said, oh, I have to do that first. So I'm going to be pretty bad about getting homework graded quickly, even though I don't have a lot of papers to grade. I just have 3 classes, numerous graduate students, committees, and life in general that keep me from getting everything done. Ideally, the ideal world is just not, can't do it all. So, and I get pinged too from other people and other places in the world asking me questions. So, Fourier transform, like I said last time, is kind of our ultimate spectrum tool for this entire class. And we have this ability to include periodic signals. And we're going to first start with energy domain signals, and then we'll move over and include power signals with the Fourier transform and the limit. So we have this as the definition. Talked about this last time, the fact that it's nice and symmetrical. The frequency domain is F in Hertz, perfect for communication systems engineers. I don't really ever have a desire to do omega domain transforms ever myself. But a control systems person might like that better. That's just their prerogative. Because they can simply say replace S by J omega, whereas I have to go a little bit further and replace S by J 2 pi times F.
Oh, the humanity.
What's that?
I said, oh, the humanity.
Yeah. How much harder is it? It's not really much harder at all. I'm just saying frequency in hertz is it the reality for me, though, in communications. So sufficient conditions, the existence of the Fourier transform. First off, it has to have absolute area that's bounded, and the discontinuities be finite. Discontinuities would be jumps that would be in the function that you're integrating. An alternate sufficient condition, which is the one we think of most often, would be this one right here, though, which just says that the energy in the signal is finite. So it's an energy signal, and that is the sufficient condition that we end up using. So once you have the Fourier transform, then you can view it as magnitude and phase, which is the most common way of doing things. So generally we're looking at the magnitude spectrum and then the phase spectrum. Occasionally there's a desire to look at the real and imaginary part, but mostly it's magnitude and phase. And when you're on the spectrum analyzer in the lab, you're only really seeing the magnitude spectrum in dBm calibrated relative to the power in sinusoid. So that's actually a little bit tricky how that comes into being, but when we talk about Fourier transform in the limit, we can also talk about how the spectrum analyzer does its thing, because it does not do, the ones we have in the lab do not do an actual Fourier transform or fast Fourier transform. They're just using a power detector and a sweep generator. So it's just the way that it's traditionally been done for most spectrum analyzers in the lab. Symmetry properties are consistent with what we saw for the Fourier series. There it was the coefficients, now it's the transform itself. So if x of n is real, which is most of the time, but not always because of what's come about as a result of software-defined radio, but if it is real, then we have this conjugate symmetry property. It says that if we look at the negative frequency axis, that's just the conjugate of what's on the positive axis. So that means that the magnitude spectrum is even in frequency and the phase spectrum is odd. When the signal is complex, it has a real and imaginary part, then this goes away. It doesn't hold anymore. So it's unique is what it really is. The spectrum will be unique between the positive and negative frequencies, and that is a really big advantage for software-defined radio in the way that it works, because it's kind of the name of the game there. And then if we happen to have an even function, then the imaginary part of the spectrum is 0. If we have an odd function, then the real part of the spectrum is 0. And that's also consistent with the properties for the Fourier series coefficients. We had Parseval's theorem for the Fourier series representation. So the equivalent or parallel to that for Fourier transforms is something that is called Rayleigh's energy theorem. First off, we know the energy is the integral of the magnitude squared of the time domain function. If I then start putting in inverse Fourier transforms one at a time into that definition, then you drop down a few lines in the development, and then pretty soon you've got yourself moved over to a frequency domain result, which when you substitute in the symmetry property, the conjugate symmetry property, which is what this but part is, finally then you get this result in the blue box that says the energy in the time domain is equivalent to the integral of the magnitude squared of the spectrum. And this will be the starting point when we start developing power spectral density for power signals. Right now, this property holds for energy signals, and it only holds for energy signals. So when we allow Fourier transforms in the limit, this doesn't quite work out the same way. We have to do something different, and that will get explained. And in Lab 2, in the COM lab, it's also kind of gone over, because Lab 2 really drills heavily on spectral analysis. the math side and then the measurement side. One of the things that I think is good to do whenever you have, say, a theorem like this is to also track out the units and just see what we're talking about on both sides, in the time domain and the frequency domain side. So that's why I have this bullet that says, are the units consistent? Do we get joules on both sides? So we know if we assume a 1 ohm impedance level, if we consider X to be a signal, it could be a current waveform or a voltage waveform. It doesn't matter in a 1 ohm system because it's either V squared over R would be power, right? Or I squared times R would be power. So it's just, we're squaring the signal itself. Let's just pretend it's voltage. We square it, we divide by 1 ohm, it's still magnitude squared. So we have the units we have up inside the integral here would be V squared, and then here we have time as our unit in there. But because V squared is effectively divided by 1 ohm, assuming a 1 ohm operating impedance, that gives us power, and then when we multiply that by time, we get power seconds or watt seconds, and that would be the same as joules, right? So the units are consistent. So this, because this goes to power, and then we have the time, so then we combine those together and the units become joules. So on the other side, in the frequency domain side, we have F, and then we have to think about what is X of F. That's the Fourier transform. So backing up over to here to the Fourier transform, what are the units of that? It's going to be volt seconds, because when you take the Fourier transform, if you want to think of that as volts, and here's T again, so the units here are volt second. Good so far? And then I square it, so volt squared times T squared, and then F is 1 over T, right? The inverse of time is frequency. They're reciprocals of each other. So then this nets out to be volt squared times T, which again will be joules, so it matches. Did you ever get taught that a long time ago? I was one of these people that never took chemistry when I was in high school. I took physics and I took electronics all my years of high school. We had a really in-depth electronics curriculum that got you advanced placement into the tech school if you wanted to go that route with your education. So I never took chemistry. I never really enjoyed chemistry, but when I first got in freshman chemistry in college, I remember they just made us work with units and units canceling and balancing units. And that was a valuable lesson for me, because I guess in physics maybe we didn't do enough of that. In high school physics, but so I always try to think that way when I'm getting stuck or if I'm a little bit confused, because thinking that way can help you solve an error, right? You're doing something, you say, let me check the units. Is it making sense? And you can a lot of times unravel something that you did wrong and get yourself out of the bind that you're in. So that's a good thing to do. So another way that we're going to be writing this then is magnitude. If I write this all the way out though, and I didn't do it that way, so let me just do a little bit more with this. So here we have, but I could also write that as volt squared per F, or per hertz. So frequency would be in hertz. So now what we have is magnitude of X of F squared is going to be called, on this page here, the energy spectral density. And it is truly a density because it's got units of joules per hertz then for its measurement quantity. And then of course when you take joules per hertz times T, and I think I messed something up here. Yeah, I didn't include the F. I left the F out on purpose. So then we can claim then that magnitude of x of f squared has units of joules per hertz. So it's called energy spectral density. So it's the density of energy spread over frequency. And those of you that are taking prop and stats right now have maybe gotten to random variables. I don't know. Have you mentioned, or are you just doing probability probably still? I mean, you can do probability for a long time. But eventually you'll be talking about probability density functions, and so that's probability spread per unit length, unit area, unit volume, and so on. So it's the same idea. It's a density, and mechanical engineers use densities like a beam has got so many, I'll just use English units, so many pounds per foot, maybe metal rod or something, and then you say, okay, so there's this many pounds per meter or something, or it could be per meter cubed or meter squared. I mean, if it's a surface or a volume or just a thin string or something. So we have density in communications, and our density is, I don't know, I could say it's the greatest. It's not the greatest. It's just very powerful though, because it has to do with meeting the requirements of the Federal Communications Commission. Will say you can emit such and such energy spectral density at a particular spot on the frequency band, and then in the band where your signal exists, your density can be whatever your regulations permit, but then the leakage that you allow outside of that is going to be such and such energy spectral density. But it won't be for an energy signal, it's going to be for a power signal, so it's actually going to be what we'll be defining later, the power spectral density for a power type signal. Remember, energy signals are typically the ones that do what in the time axes? Remember, we had periodic and aperiodic. So energy signals are usually aperiodic. Here, gone. When we're transmitting a radio signal, we're doing a continuous transmission, so that's why we have to develop power spectral density. But it's still a density, and the FCC looks at a density and saying your density has to be thus and such. And various services that are up there have requirements on density levels. I think GPS, when it first came into being, it had so much energy spectral density that it could put down in its frequency band, which it's called the L1 frequency, 1.575 gigahertz. Yeah, there's L2 also, and I'm just saying, I'm thinking of L1, that's the one that we receive with our devices.
L2 is the correction signal for the ionosphere.
Whatever, I don't remember what L2 does, but L1 is the one I think about, and you can tell I've worked in GPS a bunch, not with L2, but with L1, so that frequency has just got burned into my brain. But there was a standard that was adopted by the FCC after a bunch of experiments were run. Could we have ultra-wideband radio transmissions? So the acronym for that is UWB, ultra-wideband. And there was a time about 10 years ago where people were telling me you would go to Best Buy and you'd buy a wireless router that was going to do ultra-wideband rather than the Wi-Fi at 2.4 or 5 gigahertz. The ultra-wideband uses very narrow width pulses in the picosecond region, and it puts out a huge spectral footprint, but the spectral density is down really low. And it's encrypted by definition with a encryption code. And so the thought was that it was going to be a very secure type of local area network for your home and stuff. Some issues kept it from being fully developed. It's still being talked about, just like the optical systems are being talked about for local area networks again. But when UWB was first being talked about, it was going to spread spectrum right over on top of GPS and a lot of other services, but the spectral density was going to have it down really low, buried under the noise. But the concern was that GPS is already at a low spectral density. If we put another layer of this ultra-wideband on it, is that going to desensitize the ability of GPS to work? So they did a lot of experiments with it, and they found that, yes, it does desensitize, but you have to have a lot of ultra-wideband emitters nearby a GPS receiver. So the experiments they did was, it's like they put a GPS radio on that table there, and then they put up an increasing number of ultra-wideband emitters and just looked at what sort of performance degradation the receiver had from getting swamped out with noise that's uncorrelated from the signal, but still presents an interfering signal at the GPS receiver. It's just like I've mentioned in here, I think already, that CDMA worked that way when it was used in 3G code division multiple access. All the signals stack on top of each other, and you pulled out your signal from that stack using the local spreading code that would correlate with it. And GPS works that way too. All the signals stack on top of each other, but each satellite has a unique code. Is that believable? You don't, I mean, the spectrum, your brain says, we're talking about spectrum because we want to think most of the time it's, you're here in the spectrum, I'm over here, my leakage into your band is minimal, your leakage into mine is minimal, we coexist. That's called frequency division multiple access. The other technology that's used in cellular is time division multiple access. You're here right now, but we have a master timing signal based on GPS. You get this fraction of a time slot. I come in right after you. Next user comes in after me, and then we keep sharing that spectral resource through a time division multiple access. And then, of course, the third type is the code division, which stacks up all on top of each other, but unique codes, and the mutual interference is controlled by the uncorrelatedness of the codes. And when we talk about power spectral density, we'll be talking about auto and cross correlation. So you're going to get a chance to see what that really is and how, I don't know, I'll just say how special that is. I mean, that's a statistical property, correlatedness, that you learn about in random variables, but then you take it to a random process and use a spreading code, and that's how you can separate users. It's more complicated, but it can be done. Time division multiple access, more complicated because timing references are required. Frequency division multiple access, that's the oldest thing around. That's the logical one. You're here, don't touch my spot, but there's only so many spots to go around. That's what we ran into. Remember I said, though, if GPS fails, we're in trouble, and it's not the FDMA signals that are really going to be at stake. It's the TDMA stuff, because that's controlling when you take your turn. And if people don't know when to take their turn, it's chaos, right? I'm stomping on you. No, you're stomping on me. It was my turn. I'm just thinking about four-way stops.
Yeah, especially near a school in the morning.
Yeah. Four-way stops really don't work all that well. If there's light traffic, they tend to work. But if they tend to get like 2 or 3 cars backed up in each of the 4 directions, then people kind of don't really, they start not respecting what's going on. And I contend it's round robin, which means who's ever at the front of the line, you have to keep taking turns. But other people will say, no, my line was 20 cars long and I was here before you know what I'm talking about?
Yeah, no.
Then you have timid drivers and aggressive drivers, and it's hard.
Whoever has the bigger car.
Yeah.
No, it's positioning. Oh, you want to hit me, huh? Again.
But those ideas are present in other I'll call it technologies, how we manage traffic flow. But communications and traffic have things in common, right?
Oh, yeah.
You're talking about circles.
Yeah, roundabouts.
Yeah, roundabouts.
Yeah. Like 78% more efficient or something.
Yeah, exactly. And if you're from the East Coast, grew up with roundabouts. If you're from other parts of the country, they haven't been around for as long. That's another thing I don't think people really understand how to use them either. But they are efficient if you understand how they work and you merge in and multiplex in properly. But if you just don't, then it's frustrating. Okay, so now let's take our classical example of rectangular pulse. We did the rectangular pulse train. So now we take an isolated pulse, amplitude A, skewed by little t naught, and pulse width tau. And so you drop into the definition of the Fourier transform. So you're back up to this equation right here, and you're just going to plug into that integral. The limits go from minus and plus infinity. So you just analyze where's the action. The action's on an interval that's going to run from, when I sketch it out, I know that this pulse is sitting, it's centered on t naught, and because I know the definition of that function, it's going to run from t naught minus tau over 2 to t naught plus tau over 2. So I break the integral up, doing piecewise integration. I break it up into the region where you've got a non-zero integrand, and then everything else is 0, so you don't even think about that. And you don't think about that, right? Because you've had calculus and you just know if the integrand is 0, nothing. And then, I mean, isn't your brain already accustomed to the idea that you just automatically just see the limits are going to be this? And when you have to do a change of variables and things like that, you have to be very careful and meticulous about that, but that can be done too. And there's times in this class where changes of variables can be handy and are sometimes used in a proof. But here we just plug in the limits and then integrate the exponential, plug the upper and lower limits in, subtract, and then start massaging it around. In this case, it's the same routine as for the pulse train. There's two exponential terms after you plug in the limits, but then you can organize them so you bring out a common factor, and then you've got antisymmetric complex exponentials. So you've got an e to the plus j and an e to the minus j. And in this case, you have the minus sign in between, so you get a sign out of that. And then you have the denominator that's got the pi f tau in it, so you can form the sinc function that we saw before. And this is the thing I have in the blue box right here. This is like by rote, you know, well, by rote, this is what we've really established as the starting point. Pi of t over tau is tau sinc, well, it's a tau, never mind, yeah, I didn't have the a over here, so a is in here. A tau sinc f tau. So it's a function of frequency, and tau is a parameter, and a is the amplitude parameter. The fact that we have this thing hanging off the end, that will just remember is the delay theorem itself. So it's better at this point to just think if t naught was equal to 0, I just get the rect function becomes a tau sinc f tau, and then if we want to shift it by little t naught, we just add in the e to the minus j 2 pi f t naught. And that's from the delay theorem. That's the way I like to think of it. Use MATLAB, Mathematica, Python, whatever tool you want to draw the pictures of the magnitude and the phase spectrum. It displays the symmetry properties we were talking about for the frequency domain. Magnitude is even, phase is odd. Then I also included the plot of the energy spectral density. And this is important because the energy spectral density is the magnitude squared, and that's represents the fact that when you integrate a portion of that spectrum, that's the energy in joules that's corresponds to what's in that containment bandwidth. And of course it's a magnitude because it is energy. We would not have a signal that would produce energy in one frequency band and sort of suck energy out of the environment from the other band. Does that make any sense at all? I mean, to me it makes absolutely no sense. Signal propagating through space or down a cable or on a jack on a function generator, it is producing energy. If it's a single pulse power signal, it would be power, but for a single pulse it would just be a blip of something that would correspond to so many joules coming out for that single emission. So energy spectral density would just tell us how it's spread over frequency. So now getting into the theorems, we have basics like the superposition theorem, and I left a space in the notes here for just writing out the proof, but does anybody have a problem wanting to write that proof out on their own? You just take and apply the Fourier transform. I mean, basically what it comes down to is if I just say I'm going to do this, I'm using what I know is true for a linear combination of functions put inside of an integration formula. The superposition idea for integration just comes from calculus. It would say constants factor out, and then I'm able to move inside and make the Fourier transform operator hover on the time domain function, and then we're just operationally saying that Fourier transform of x1 of t becomes big X1 of f. So that's pretty straightforward. Delay theorem is also straightforward, but I'll work this one through just to say I did one of these. So if we want to just establish the delay theorem, we would go ahead and say formally starting off like that, and then plugging into the definition. And then I'm just going to make a substitution, let lambda equal t minus t naught. D lambda equals dt. And you see where I'm going? I'm just doing change of variables in an integral. So now I can go ahead and do this step, but in order to even do that step, writing the limits, I have to then say under the new variable lambda, as t goes to infinity, for a finite value of t naught, lambda is also going to go to infinity, right? So the upper limit is still plus infinity. In the lower limit, under the new variable lambda, the same thing holds. T goes to minus infinity for t naught fixed. So the limits are fine. This is now x of lambda. And then I just end up making the substitution in here, minus 2 pi f. And then in place of t, I'm going to say t is equal to lambda plus t naught, right? Just rearranging the algebra there. And then that's d lambda. And then there's only one more step. And that step is simply factoring out the e to the minus j 2 pi f t naught. Then you're left with just x of lambda times e to the minus j 2 pi f lambda d lambda. And if you don't like the lambda, you could just put t back in there in place of it, because it's just a so-called dummy variable, one that's just being used to carry out the integration. So this is the definition of the Fourier transform, so that's just the x of f. Things like this, sometimes I put on the exams, just say, do this, verify the simple theorem, or check this. So check some property. Good? So the delay theorem is used a lot. The frequency translation theorem and the modulation theorem are used even more. So the modulation theorem is kind of at the heart of communications theory because we're all about modulating information onto a carrier and then demodulating it off of a carrier. So we're going to be using the modulation theorem a lot. And it's reminding me of a guy who sounded like he had, I think, an Italian sounding name or French name, I don't remember which. He wrote to me about my Dummies book. He said, do you mind if I send you a bunch of questions? I'm like, do I have time to answer questions for somebody somewhere in the world? So I said, I'll consider it. Where are you located? Because it's like I want to know where they're at, 'cause I'm just curious, where did they buy the book and that kind of thing. He's in South Carolina, Charlotte or something like that. So he did send me a bunch of questions. I got them on Saturday morning. It's like that long. And the questions are very abstract. They're just kind of, he says, I'm a newbie. So the first question is, I have a signal, x of t, and I want to write it as a complex signal. So I have x of t, or x sub, I'll just say x sub r for real part. And then he said, I'll have an imaginary part. I'll call it x sub imaginary, or he used different letters. But he said, how do I choose that signal? And I started trying to write back to him. It's like, well, he's thinking on a different plane than me. It's like, how do I choose that complex signal? I mean, what he wants to know, can I make it anything I want? And I'm like, I just don't know exactly how I want to answer that. I've got to look at the second problem. He's going somewhere with, but I don't know where. It's like, I can freely pick that, right? Or no. It has to, in my mind, it has to be motivated by something. So right now, in this example, you wouldn't just say, I'm going to put an imaginary part next to my real part. We are going to talk about the analytic signal idea and how we might do something with the Hilbert transform. We're going to see that unfold a little bit. So I don't know whether he's going in that direction, but it strikes me strangely because it seemingly comes from out of the blue. Just zap, there it is. I don't think any of you would start there, would you, if you were going to ask a question? It was like, sure, if you're reading my book from the front cover and then this thing comes, it's like, where did you get this idea from? Obviously tainted by some previous experience. It's just, I mean, that's kind of the reason why I said I would do it, because I'm just interested in perceptions, but I didn't expect it to be quite as far off center as that.
So is this what you call up conversion?
This would be up conversion, but really in the modulation theorem is where it'll be that. So first I'll just walk through translation. Translation is where you multiply times a complex exponential, complex sinusoid, and what that does is it takes the spectrum and it shifts it up. So if the spectrum starts out at baseband, comes out over here, shift it up to f naught, just like that. So if this was x of f, then this is the shifted version. It is up conversion, but it's not up conversion in the typical radio sense. In software-defined radio, this would be up conversion. But what we've done by multiplying by a complex sinusoid, we've created a signal that's complex. So you can see how easy it is to go from a real signal, has symmetrical spectrum, and now what have we done to it? We just broke the rules. I mean, we created a complex signal because of that spectrum over there on the right. You don't see an image at the negative frequency. It's definitely got a different character. It doesn't have an even spectrum. it's cool what we've done, and software-defined radio can do these sorts of things, but what it's going to do is if it's going to radiate it through an antenna structure, it's going to end up just taking the real part of that. And that is what the modulation theorem does. So the modulation theorem starts off by saying we're going to take the real part, and if we take the real part of the complex sinusoid, we just get the cosine. So when we multiply by a cosine, then we will shift half the spectrum up in frequency and half the spectrum down in frequency. So we get this operation, and this is the upconversion idea for real signals. It's saying we have a real signal, we're going to upconvert it to a different frequency, and of necessity, because it's going to maintain itself as a real signal, and you'll do this in the comm lab because the board, the RF board, has mixers on it, or multipliers for doing signal multiplication. So we'll get a copy at F0 and a copy at minus F0. In software-defined radio, though, we purposefully can do up and down conversion into the complex domain, and then when you get ready to transmit it, you can finally take the real part with some other manipulations thrown in there along the way, filtering and other operations you might want to do. But a real signal, whether it's a baseband signal, and when I say baseband, I mean centered around DC. And then this is an RF, or it's called bandpass. So bandpass domain signal is still real, but in order to maintain the symmetry that we've been talking about, it is going to have the two spectral images. Now, the negative frequency, remember, is just an artifact in our mathematical modeling. It has to be there mathematically. When you tune in to receive this signal, you're not receiving at negative F0, you're actually mixing it back down again with a plus F0 or some other positive frequency. But again, software-defined radio adds different twists into things, which makes this classical type of result here kind of get somewhat rearranged. Nothing is done to harm or make things harder. Things are done in software-defined radio to make things easier and make them more efficient. But this is where we have to start. If we started over there, it'd be more confusing, is my feeling. So is that looking good so far? I'm going to switch over to the Jupyter Notebook and do some things with that pretty soon. But then another useful result is the duality theorem, which just says we can interchange roles of time and frequency. And so any theorem we get going from time to frequency can also be flipped around to go frequency to time. So the duality theorem just says replace little x by big X, and that's going to make it look like we're inverse Fourier transforming a Fourier transform, which means what we're doing is we have this extra minus sign in there, so when we get back to the time domain, we have variables swapped around. We use the duality theorem a lot in this class for this particular case, where we have a rectangular pulse in the time domain, and that was a sinc function in the frequency domain. If we want to model something that has a nice band-limited spectrum, we can use the duality theorem and say that I know that if I transform a rectangle, that becomes a sinc in frequency. So if I inverse transform a rectangle in frequency, that should take me back to a sinc in time. And we can see, because we have that minus sign, but the sinc function is even, everything just sort of falls back into place. So we have this result right here, that 2W sinc 2WT becomes a rectangular spectrum. And this is a useful idea for modeling purposes, to say that we have a band-limited spectrum. We can't really produce the time-limited. The sinc function has got tails that go off to plus and minus infinity, so it's definitely not causal. It doesn't start at t is equal to 0 and go forward. It's been present for all time, and it's present for all future time. but we can approximate that idea and just say this is a test waveform, and we can just play games in modeling with the rectangular spectrum. So that gets used a lot in modeling. I mean, something that I know makes this class, I guess, hard and abstract is we will use the rectangular spectrum just to prove out concepts, to see if this idea is going to work with this idealized spectral model. And then if that's still looking good, then we can proceed forward and say, okay, now let me put some realistic assumptions in here and take out these perfectly band-limited spectra and see are things still workable at this point. And you'll get exposed to that in the project as well, the first project in particular. I guess maybe I want to ask the question, do you see any problem with that? I mean, you got to start somewhere. So do you want to start with the most realistic system and have all these little intricate details that could keep you from seeing what's making it work or what's breaking it? It's better to start with something that's got a lot of simplifying assumptions just to see, are these concepts solid? Are things looking good? And then start replacing the simplifying assumptions with some realistic constraints and then see if that's workable. Your idea of engineering and mine are two different things only because I've had more experience, right? Once you've been there and done that, almost anything in life, if there's something that you didn't like about the way it turned out in the end, do you repeat that process, or do you say the next time I'm going to do this, but I'm not going to do that one thing that I know led to some irritation or some dissatisfaction, like don't drive to Denver during rush hour or something like that. I mean, unless you have to. So there's a lot of that will be going on in some modeling. So this is a handy result. So it's just flipping things around. And just to see the differences in this, remember we had before we had this became tau sync f tau. So this is just a little bit different, and what makes it different is the signal is defined as a baseband signal, and we know we can't just say a real signal can have a spectrum that only goes from 0 to W, because it has to be even in frequency, right? I mean, the magnitude has to be even, so we have to define it over the entire interval and make it symmetrical about 0, so we pick 2W, so the low-pass bandwidth. Is W, but then that forces us to have the 2W in the rect function, and then that comes across over here and forces, oops, screen moved at the wrong time on me, forces the 2W over there, but it's still consistent, right? Here we have tau, and here we have tau. So in terms of what has to be locked in your brain, it's 100% consistent. You just have to keep everything lined up. Tau, that's what we use it for the time domain, rect to sync, and then to go backwards from rect to sync, we use 2W because that's a more useful representation. There are other theorems. There's differentiation theorem, which occasionally is useful, and we will use this idea when we're talking about modulation theory. The proof of this theorem is a little bit more tedious. It requires an integration by parts, and I have it sketched here, and it's in the book. I don't really want to drill into this. It brings back memories of one of my college roommates in the dorm singing his little jingle about UV VDU when we were both taking calculus. Did anybody have a jingle to remember that by? Or not? Okay. Okay. I can think of my roommate's thing, but it's not something that's nice for me to say. So it was just something he made up that's,
That's cool. My kidney's not a bad influence.
yeah. You didn't introduce him, but I figured you were related.
Yeah, I know. Could you tell?
Yeah. You can also use Leibniz rule for differentiation of integrals, and so I have an alternate proof in here, which I tended to like better. And Leibniz rule shows up in Prob and Stats. Actually, you'll get a chance to maybe see it if your professor decides to use it. I like using it myself. When you have to integrate a CDF function to a PDF function, you sometimes have to use this property, the Leibniz rule formula. So now we can actually apply a theorem, though, and we can do something with the differentiation theorem, too. So Fourier transform of a triangle pulse is something we're interested in getting our hands on. So we have the triangle pulse defined earlier. It formally gets defined here in my notes, which is my mistake. I should have it up earlier, and I penciled it in earlier. But if we use a differentiation theorem on this, we can choose to differentiate operationally the triangle pulse once, and we'll get 2 rectangle pulses. If we decide to differentiate it a second time, we'll get 3 delta functions. So in this case, I chose to actually differentiate it twice, and then Fourier transform the third representation, the double derivative, and then unwrap it by dividing by j2 pi f quantity squared. And when you do that and reassemble the 3 terms that you get, you end up getting a sine squared. So you end up in the end getting a sinc squared. And this is memorable. And maybe this is, this also relates to the definition of the triangle. Remember, the base of the triangle is 2 tau, whereas the rect, it's just tau. But when you transform this triangle into the time domain, you still get tau times the sinc, except now it's tau sinc squared, f tau. So this week's quiz will likely have something with rex and tri pulses, and sinc squared will be things that you'll probably want to know. It is, that info is on your crib sheet, though. There's the Fourier transform table, and then theorems are on that cheat sheet. Trying to think what, I have an example that's coming up here, but there's something kind of interesting about the triangle versus the rectangle. The rectangle gives you the sinc function that is going positive and negative with the tails, whereas the triangle, interesting thing is they both are pulses that are above the time axes, but the triangle, its spectrum is purely non-negative, because the sinc squared, it's always going to be sitting above the axis, so it's a non-negative quantity. And we'll be seeing that when we talk about power spectral density too, that when we choose something to transform involving a power spectrum, we have to choose primitives in the time domain side that end up being non-negative on the frequency domain side, so that energy spectral density and power spectral density will be non-negative and obey one of the properties of a spectral density, and that is you cannot pick a slot in the frequency axis where you look at the energy spectral density and you end up with a negative number, because that's just not, remember I said a little while ago, that's nonsensical. Generators producing a waveform, and if you could actually find a piece of the spectrum that was returning energy back, it'd be like you just discovered something that really gripes me when politicians talk about renewable sources and everything. I have a problem with that, because I have a problem saying I don't think we have free energy unless it's coming from the sun, and that's got to be harvested. But if we had a means of producing a signal that actually we could integrate a part of the spectrum and it would produce power to us that we could use. Doesn't that seem bizarre though? It's like free energy. I just don't think there's free energy around. We have to harvest it somehow or another, but that's just me.
Some have less effort.
What's that?
Some have less effort, and others have less cost.
Oh, to get to the energy?
To the energy.
Yeah. Well, I also, since I shop at the Vitamin Cottage Natural Grocers with my wife, they stopped putting out the same plastic bags that they were using for the produce department. They have a new bag that's made out of plant material. And when she said it's made out of plant material, I said, well, wait a minute, where did oil come from to make plastic? It was decomposed plants, isn't it? So I'm a little bit confused why when she said it's plant material, because it has a similar origin. It's just one is newer plant material and the other one's very, very old, been around for a long time. I just found it interesting, but didn't like the bags because the bags don't seal very well. So you put a piece of bread in the bag because it can decompose rapidly, and guess what happens to the bread inside the bag? It turns to toast in a matter of a few days because the bag breathes so much that it has a totally different property. And people complained about that, and I had to learn my lesson the hard way. And then the next time I was in the produce department at the store, they said, if you use these bags, be aware of the fact that this and this and this is going to happen. And I'm like, yep, I noticed that right away. I had toast because it dried things out, but it will disintegrate in a landfill quickly though. Okay, convolution is a very important property, and it just says in the time domain, you learn about convolution in 3205 and earlier. When you convolve two signals, you go through this convolution operation, and in linear time invariant systems, the convolution, of course, is usually what we're talking about when we have a system and an impulse response, and that comes up a little bit later in the review. But if we had an x1 of t, and this happened to be the impulse response, which is a time domain function, then this would be, say, y1 of t, and that would be obtained. That would be the system, or signal x driving through a system with some impulse response, but it's a time domain waveform. And then the convolution integral gives us that convolution. And then a special case of a delta function just sips out the function. This is, I just highlighted this at this point because we will definitely be using that to an advantage. There is one convolution problem on the homework for this week, but I'm not going to be quizzing over that because we're going to get into that more in a separate part of the review. But the convolution theorem itself, which is going to be talked about, I guess it's right down here, tells us that when we take the Fourier transform of both sides, we end up with the important result that the convolution of two signals in the time domain is the product of their individual Fourier transforms. So that ends up being super convenient. We can just multiply rather than having to convolve, and then if necessary you could inverse transform the product. So I first go through an example here, and I'm going to not do this because I want to talk about the homework, but I will be talking about this next time, and I'll also be talking about revisiting the problem of convolving two rectangles. And when you convolve two rectangles, you get in the frequency domain, you get a sinc squared, and then you find out, oh yeah, that leads me to the triangle function. And that's why the triangle function is defined the way it is, because now the base width of the triangle is 2 times tau. So I think that's why Dr. Ziemer has it defined that way. Okay, to talk about the homework, and talk about what's posted on the website right now. First problem is a drill problem, and it's just on properties relating to Fourier series. So this is quizzable material for the quiz on Thursday. So I'll put up the solutions to the problem, but this is good, simple things to ask you questions about. Number 2 is a simulation problem, and I do want it to be turned in. I'm going to tweak the assignment sheet here, but I just wrote it in. It's problem 222, which I kind of looked at, and it is also already in the Jupyter Notebook. It's partially built up in the Jupyter Notebook at that. But rather than having to get the Fourier coefficients by direct calculation, or as this problem says, using the table, what I want you to do is actually set it up in the notebook so you just do it numerically. And it's just so you get used to the idea that sometimes you might want to do something numerically. So you're going to be using the FFT, and there's an example in there, and I hope to jump to that shortly here. And you'll just get the idea that, okay, I'm just going to create one period of the waveform, and this is going to be that one period. So this, you're going to synthesize a waveform that does something like this. I'm assuming in this problem, just for simplicity, that T naught is equal to 1 second, just for convenience. So you're going to write a function called trap pulse. And you can use one of the examples in the notebook that I want to point at to do that. The second part of this problem asks you to find the relationship between the two pulses in the book, the A waveform and the B waveform. But when you're actually generating the line spectra, what I want you to do is take the signal generated by trap pulse and just modify it. So if you create a signal that looks like this, and then if you want to create a signal that looks, I have to go look in the book to make sure I know I've got this right. Yeah. What the book wants you to do is then create a signal over one period that looks like that. So that the tau is now shifted over here. What you're going to do is you're just going to take your one period definition and do some addition and multiplication to just flip it over and change its orientation. You might load in 1 minus tau or something like that. But you're going to be able to generate that pulse, the bottom line. And then you'll be able to numerically get the Fourier series. So I give you some hints, and because I now have an Apple Pencil with an iPad, I decided to draw this stuff out. So this is what you're trying to create, and the book problem wants you to do it for tau equaling T naught over 4. So tau is going to equal to 1/4 in this case, since I've already said that T naught equals 1. And then you're going to write a function. I called it 1 pulse. Synthesize it on a time axis, so you've got 1024 points on that 0 to 1 second. And then you put in, the function does that synthesizing, and you put in the number of points you want on the interval 0 to 1, put in tau, and then it returns the pulse. And I had it return, this is a cut of what I have in my notebook, because I didn't want to show you everything because it's my solution. I just cut out sort of a piece of it so you can see how I did it. So I said xp equals x for the first waveform, the A waveform, and then I just massaged it a bit with some algebra to get it into the other form. And then I take the FFT of it, and I have to do some normalizing on that. And I didn't show that either, but that is talked about right up here. You just have to divide by n. So where did I write that? Yeah. Once you get the FFT points, you'll divide them by n. And then you can there's a waveform, there's an example that I ran, and then there's the line spectra result right there. Look okay? I just want you to take this for a test drive. If you are just up against the wall with Python and you just want to revert back to using MATLAB for the time being, I'm okay, just get something done, but this is to kind of get you bootstrapped into taking Python for a test drive. And in terms of how you're actually going to generate it, I have this example in here of the line spectra, and put it in the presentation mode. So here I did a line spectra plot where I got the Fourier coefficients theoretically. So here's an example in my notebook here where I just plugged in the theoretical value, but you're going to put in a calculated value. And an example of how to do that is down here in this example for the trap pulse. So here I have a function called trap pulse that generates the samples, and then I load them in. Here I divided by n when I actually did the line spectra plotting, but I think it's better to just divide by n up here. So this is a template for what you want to do to generate the line spectra. And then this is the template for what you want to do to create the rectangular pulse. You could do it other ways, but I'd like you to do it in a function, so the function will have the interface that I'm describing over here. It will take n, the number of points, and then the pulse width tau as the second argument. So how are you going to do that? You can hack this function right here pretty readily to follow along. This tells you how to set up the time axes, set up a dummy array filled with zeros, and then all you really have to do is you just have to modify this if-else. I can tell you right now, your code is basically just that first if block. And then the rest of it is not needed because Python will just leave the zeros in place, and that's all you have to do.
So,
You have to tweak this some, but
so do you want us to just butcher this stuff into our own notebook, or
Yeah.
just to play with it in the chapter 2? And then screenshots
well,
of our new outputs?
either way, just as long as I can get documentation of what you did in your whatever you turn in.
Okay,
So you can cut and paste if you want to do it that way. If you want to just create a new notebook. If you're using Jupyter Lab, another nice thing about Jupyter Lab is if you just copy this notebook or you start a new notebook, you can copy the top cells, and then if you want to copy the selected cells, and then if I shift it over to another notebook, I could paste the cells right in there. So there's things you can do that are kind of convenient. Sound okay? It's a very easy thing to do, and I just want you to, I want to give you something to do that it'll build your confidence. So this is a confidence building exercise. You can get at it different ways. You can do what the original problem statement said to double check it, but I want you to just say, wow, it's pretty easy to just numerically do it. I don't always have to use detailed, Fourier series formulas. So the other problem that you have to turn in this one is a very practical problem. In digital communications, at baseband, and then we move it up onto a carrier, but just at baseband, we will send a sequence of bits, generally in bipolar form, so plus and minus ones are used to represent a bit stream, and then we will send a pulse of, say, so many seconds duration, but we'll start off sending a new pulse every capital T seconds, and 1 over that will be the bit rate. Everybody's familiar with the idea of bit rate, right? Because you have bit rate in your Wi-Fi and cellular telephony, et cetera, et cetera. So you're probably thinking megabits. I could be thinking kilobits. Or in GPS, it sends down 50 bits per second of ephemeris data from the satellites to the GPS receiver. 50 bits per second. It doesn't sound very useful, but the information gets there and the receiver gets to know what's going on the satellite, where it's exactly located in the sky, which is very important. At any rate, pulse shaping is used frequently. So pulse shaping via a square root raised cosine pulse shape is pretty common in cellular telephony. And this kind of exotic looking thing is the pulse shape that is used a lot, and it has a parameter called excess bandwidth, which controls the shaping of the pulse. Alpha goes to 0, and the pulse has got a spectrum that's very, very compact, almost like the rectangular pulse. And it is, as a matter of fact, because this becomes a sinc function as alpha goes to 0, but we can't build that because the pulse has to have a very long period to it, or a very long implementation in memory. So we pick alpha values, and I'm having you compare alpha values that are 0.25 and 0.35. So I did an example here with 0.5, I think. No, I did 0.25. I did part of the problem here already for you, just as a template. This problem is easier in some sense because I give you almost everything, and here you just have to use some functions. In SIG-SYS module, this impulse response, or this pulse shape function, gets defined, and then I have numerically a way of getting the Fourier transform of that pulse. So that's another function that's available in the SIG-SYS module. So I'm using that to approximate the Fourier transform, and then plot it in decibels, and then overlay the plot. So you're going to overlay another plot on top of this. And then what I want you to do is verify that the two-sided bandwidth is when you square the magnitude of the spectrum, which is sending it through a square root raised cosine filter on top of the pulse shape, and talk more about that later. But we'll actually, it's like we square root raised cosine send the pulse, and then we do the same thing at the receiver. So we do it twice. The bandwidth of the pulse is nominally what's shown here. It's a full-sided bandwidth of the bit rate. Remember, bit rate is going to be 1 over t. In this case, it's unity. The bandwidth of the pulse is approximately the bit rate times 1 plus alpha. So you're going to get another curve like this one laying right up against it. And what I want you to do is verify that that drops down, in this case, to 0.75, because that's half the width. And then the other pulse you're going to do is 0.35. So that's going to be a little bit wider. So it's going to be hanging out in here. So what I'd recommend you do, since you can't move a cursor around very easily, is just overlay a vertical line on the plot where you think it should be theoretically, and just see, does it match up with what your calculated plotted value is. If you're not following me on that, I'll show you what I have done in my solution as you're heading out of here, since I've got it. I've got my solutions right here. This is the two pulse shapes at the top from a distance, and then the corresponding spectral shapes are right there. So one of them is already in the picture, but you'll generate it, and then I have a vertical dashed line that I just overlaid in my plot commands to just draw a vertical line next to it, and then another one for the second pulse next to it, and they're sitting dead on where they're supposed to sit. So give that a try. Ask me questions if this is confusing you at all, but this is a practical pulse shape called
This is due Thursday?
yeah. I'm keeping you busy, but it's not intense. And then there's another Fourier transform problem, but there'll probably be something with properties of Fourier transforms. There won't be anything like this. There'll be something with Fourier series. I'm gonna keep it on the light side. You will have to do something, and you'll probably have to use your theorems table. I'll probably have something with rect and tri, the things we talked about today, and some properties of Fourier series. Like if I give you a waveform and say I'm going to shift this, how are the Fourier coefficients going to change? Remember the theorem we talked about last time? If we would have gotten shortchanged, I would have had to shift my schedule, so I'm glad we didn't have a snow day today.
So problems 2 and 3 are the ones being turned in for homework?
Right now, it's 3. There's 3, yeah. One is just pencil and paper Fourier transform. That's 2.29a only. That's just writing out the Fourier transform of the sum of 2 signals. That one's pretty straightforward. Easy paper problem with the transform tables, and then these 2 numerically oriented ones. And they have different flavors. Second one, I'm giving you almost everything. You've got to just figure out how to plot it and get the matchup that I'm looking for in the bandwidth. And the second one, you've got to put a few more pieces together, but it's not really very much. And I have examples in that notebook. If you can't run that Jupyter notebook, yeah, you're hosed right now. So you got to be able to run it. So I'm kind of twisting you and saying you got to get a Jupyter notebook to open up so that you can play with the one that I have up there posted. That unlocks the ability. So I'll take questions in my office. I'll take questions, I guess, online as necessary to help you with it. How many people don't have Jupyter Lab or Jupyter Notebook running yet? So everybody's got that part done, right? Okay, so go forth and produce is what I'd say. I think you can do it.
Okay, 2, 3, 5.
Okay, yeah.